timer. No. Did I just say set a timer? Welcome back to linear algebra, all right? 2 flashcards. What do we got? What is the trace of a square matrix? It's the sum of the entries in the main diagonal. And how is it denoted? It's denoted by TR. In parentheses, you put the matrix. What is the transpose of an MXN matrix? Now it's denoted. You essentially switch the rows for the columns. So there's going to end up being N by N, M rows. The rows become the columns become the rows. It's denoted by to the power of capital T. All right. All right. All right, I'm gonna grade what I did yesterday, then I'm gonna be back in a second. All right. This one we got right, the 1.2. We showed this. Oh, wrong page. So I'm not gonna go through them. I'm gonna keep moving forward. We got them right. Now I'm gonna continue working on this proof I was working on. I'll be back at the end of the day. This is weird. I finished all the problems. All right, we're done with 1.3 or 1.4. We're about to jump into 1.5 after explaining these. So this is, hold up. We had 2 proofs. This was finishing this one from yesterday. Basically showing that these are equal if A, B, and C are the same size. If A, B, and C are the same size, well then we can say based on the definition of addition that A plus B plus C is going to be, the resulting entries are going to be A plus B plus C with the sub ij, these entries. And basically the same thing for this, and we can say that those are equal. Why? Because of the associative law or property of addition of real numbers. And then if they're the same size, which we know they're the same size because we can add them and the products or the sums defined, and the entries are equal because of the associative property of addition, then we can say that these are equal, and that is a valid statement. Maybe even easier here with A minus 0 equaling A. Basically, we're trying to prove that if they're the same size, then this statement's true. We can say that if they're the same size, then the products are the sums defined. If the sum's defined, then the matrix, resulting matrix can have entries of A sub ij minus 0, which is equal to A sub ij based on the property of subtracting 0 from a real number being the original real number. And since we know that they're the same size because the product or the sum was defined, or the difference was defined, and that all the entries will just be A sub ij, well then it's really just A, and so A minus 0 is A. Then we did true or false. It was basically asking if A plus B squared equals A squared plus 2AB plus B squared. No, it doesn't, because matrices don't always commute. Right, if a row or column of a matrix, they're just saying is the determinant, does the determinant have to not equal 0 for a matrix to be invertible? Yeah, just based on the definition we learned of how to know if a matrix is invertible. And then similarly, if a row or a column is all zeros, is a matrix invertible? No, because the determinant's always going to be equal to 0. So, boom. I'm going to start reading this next section now. 1.5, which is elementary matrices. I don't know what are elementary matrices. I don't know. And a method for finding the inverse of A. So I'll be back in about a minute. We're going to read really simply, really quickly, because we're going to run out of time. Just starting the next section. So this is exciting because it felt like we were never going to finish that last section, but we're through. I'll talk to you in a little bit. So we just started reading this section on elementary matrices. Haven't learned what they are yet, but they brought up 3 elementary row operations, which we've got down pat. Interchanging 2 rows, multiplying a constant by a non-zero constant through a row, and also adding a non-zero constant times one row to another. And so they said, well, given that, it should be, you know, kind of evident that there are three elementary row operations that specifically undo an elementary row operation. Basically, one is multiply the same row by 1 over c, c being the constant, non-zero constant, interchanging the rows back, flipping the rows back, or subtracting a constant times the row to the constant times the row that was to the row that had a constant times a row added to it. So undoing the elementary row operation. So that's the beginning of this section. It looks actually pretty quick. Not quick, but short. Only like 5 pages, it looks like, for this section. So that's kind of refreshing. There's been a lot of reading up to this point. Oh my gosh, yeah. 5 pages. So that's it for today. Talk to you tomorrow. See ya.